roller bearing. Roller bearing is a type of a rolling bearing. Roller bearing is a type of a bearing where the elements are cylindrical in shape. But rolling bearing means any kind of bearing that has mechanical elements which rotate between the static and rotating part of the system. So about the lifetime calculations for the bearings, which is I would say the basic thing for an engineer to understand and to do and to perform for bearing assembly when designing a machine or component of a machine which contains bearings. You would need to check at least some of the characteristics of the bearings against lifetime. And there's a standard ISO 281 and further on more advanced ISO 16281, which describe the calculation method for bearing lifetime. And the lifetime is given as a value L equal to something, and it could be either hours or it could be revolutions. And this L is usually equipped with a subscript which defines certain information. So first there is a subscript which contains a number, and that number indicates what is the failure probability of the bearing considering those loads and all the other parameters that we use in the calculation. So for example here, if we have a designation L subscript 10, which that would mean that statistically 10% of the bearings would fail with those loads. And if this number would be 5, it would mean that 5% would fail statistically. And someone might consider, okay, 10% failing bearings, it's a lot. Yeah, maybe. But when you consider the Gaussian distribution, in order to obtain higher statistical reliability for the bearing system, it would probably mean very high over-dimensioning for the bearing system in order to gain better statistical probability against failure. So, for example, if you go from 10% failure probability to 5%, it would mean that basically your loads needs to be around 25% of the 10% loads. So it's quite a drastic change in the loads and also in the bearing size. And usually even 1% is L1 is very rarely used. I've only seen aerospace application where L1 is being used. So 99% failure probability is already very, very high. And quite normal is L10. In some cases, maybe L5, but usually L10 is quite well sufficient for most everyday engineering cases. And if you have the letter after the number, if it's N, it means that the lifetime is given in revolutions. And that means that it's in the millions of revolutions. So if the L, for example, L10N would be 5, it would mean that the lifetime would be 5 million revolutions. But if we have a letter which is H, then we have calculated the value according to the hours of the lifetime. So it includes the effect of the speed. And I'd say that in most cases, this L10H is being used because most often we want to know what is the lifetime in calendar time. So therefore, L10H is the one that we would apply. In addition, there could be some other subscripts as well, like M, which stands for modified. And that means that we have included some lifetime adjustment factors, such as lubrication in the calculation. And if it's R, it means that it's the reference rating life. So then it will include also the load distribution inside the bearing. So it's already fairly sophisticated method for calculation. We'll go to check that later on a bit more detailed, but now a couple of examples of bearing configurations. By the way, you can find this presentation already in the Moodle if you want to check it from there. So bearings are used in various many applications. So maybe one of the most common would be a passenger vehicle bearing system, which is, for example, in this picture. So you have here the rim of the wheel, and the tire would be over here, and then there's a hub, and you have in this system there's 2 times tapered roller bearings which take the loads from the road and from the mass of the vehicle and passengers, etc. In here you can see a bearing system which is containing only half of it. So there's one deep groove ball bearing, and there are some cavities which can contain grease and also guide the grease away from the bearing system. And this bearing is, in this case, it's open, which means that there are no seals on the sides of the bearing, which means that when we feed lubrication grease from here, it can freely enter inside the bearing. And then, of course, used grease can eject from here, from the grease relief. Here in the lower right-hand side, you can find a bit more special type of bearing configuration. So there are multiple angular contact ball bearings. So this type of bearing where you can see the force line inside the bearing is skewed. It's not directly against the shaft, but it's in angle. This is called angular contact ball bearing. And in this kind of setup, it's probable that there's very high loads, and therefore they've been using several angular contact ball bearings in a series. Not the most easy configuration, because it's in many cases quite difficult to control that this kind of bearing system would distribute the loads onto each of the bearings in a defined manner, so that you would be able to calculate what is the exact load for each of the bearings. If you have several bearings which can take, for example, axial load from right to the left, like these bearings over here. If the shaft is loaded from right to the left, these 2 bearings both carry the axial load, and it is quite difficult to, or impossible to, calculate what is the load of an individual bearing, because it's statistically undefined construction.
What are those small channels? Are those for lubrication?
You mean these?
Or? Yeah, and also on the opposite side. Yeah, these channels.
Yes, I would assume that these are for lubrication. So this kind of bearing systems are also used in grinding machinery, and it could be that this is either input or output for a lubrication oil.
So it's is it added only when needed or constantly?
If the lubrication is done with oil, it's usually constant, so, or at least intermittent. So there are a pulse every maybe 15 minutes when there's fed oil, or then it's a constant spray or constant drops of bearing. Especially in this kind of, I would say that this configuration contains fairly small bearings. But if the bearing size is large and if the bearing rotation is fairly low, there could be also this kind of oil bath lubrication, which means that part of the bearing housing is filled with oil, and these lowest bearing elements are sort of submerged in the oil, and that will eventually create the oil to distribute all over the raceways. But usually the oil application is done with a pump, and there's a more or less constant distribution of the oil.
Sorry.
Thank you.
Yes, go ahead.
Can I ask what is the main function of the anti-churning vanes in the second configuration? The grease relief and the anti-churning vanes.
Okay. This is I have to say that what is the meaning in this application? Sometimes they've been used so that they will help the grease to get out. So because there is sort of a flap or it's a sort of a blade, so it will help the grease to get away. So I have to say that I'm not quite sure how in this construction it's been done, but sometimes they've been used so that it will help the grease to get away when there are certain veins. So if it's not smooth. So this will sort of prevent because in some cases the grease tends to pack in the cavity behind. So it could be that, but I'm not 100% sure of this. Now that I don't know what is the PLS construction. This is taken from a web source, and I don't recall what is the PLS. It's a machine or of sort where this picture is taken of. Okay. A bit more bearing configurations. This is quite typical configuration for a spur gearbox. So in a spur gear, we have a straight teeth, which means that we don't have axial loads. So in that application, deep groove ball bearings can work quite fine. And for some reason, this gearbox is been designed so that this bigger gear wheel is a cantilever. Sort of it's hanging outside, not in between the bearing distance, but outside of it. And therefore this, of course, this front bearing is more loaded, and that needs to be bigger. Another type of bearing system, like in gearboxes, if we have, for example, helical gears. Helical gear means that the teeth are in angle. That will always introduce axial force to the shaft, and we have to have a bearing configuration which can carry the axial load, and that can be done, for example, with a pair of tapered roller bearings like here. So here we have rolls which are rotating in an angle. So the inner raceway and outer raceway, they form a conical surface along which the bearing is rotating. But characteristic of this bearing is, of course, that this kind of bearing can only carry load in one direction. If we would have just this bearing alone, and there would be force from right hand to the left side, it would fall off because there's nothing to carry the load. So it's unidirectional bearing. And for that reason, we had to have some other bearing which can carry the load in other direction. In most cases, it's another taper roller bearing, but it can be also, for example, a pressure bearing. Okay, here we have some options how to secure the bearing onto the shaft. So here we have a different kind of circlips so retaining rings. So there's a groove and there's a retaining ring. Here we have a retaining ring, which is how to say, it's there's a shoulder, it's not straight. And here we have a additional collar, which is used to press against the bearing. Or we can just have a flat plate, which is then bolted against the shaft end, like here. Or in quite normal cases, there are shaft nuts, which are tightened onto the thread on the shaft. And the shaft nuts are, and it needs to be secured some way. And in many cases, they are secured with this kind of lock washer. So the shape is like here. And when you have these extensions of the plate, you can bend them onto the grooves of the shaft nut, and that will prevent the shaft nut from rotating. Of course, the inside, how to say, extension of the shaft nut needs to go into a groove in the shaft, so that it would perform the locking function. So there's a groove in the shaft where this flip is going into. Okay, last time we discussed something about the sliding bearings, and when you're designing a new machine, you had to consider what kind of bearing system you would introduce over there. And you would maybe think, would you use either rolling bearing or a sliding bearing? There is not a clear direct rules how to apply it, but here are some considerations that you might want to think when you make the decision. So a sliding bearing is a simple and inexpensive type of the bearing if the load and speed is low. As we spoke last time, like if we have a mechanism which has fairly small loads and fairly small speeds, and that only needs to perform rotation and carry loads, then the sliding bearing is probably the most inexpensive and good solution. But if you have higher loads, high speeds, then hydrodynamic sliding bearing would be maybe better. And if your bearing system or machine needs to tolerate very high vibrations, then hydrostatic bearing would be the best. If you need very low operation speed in conjunction with resistance to vibration. Also, rolling bearing can take vibration while it's running, and especially if it's running very fast, it can take fairly high vibration. Like in two-stroke machines, they use needle bearings in the connecting rod between the piston and the crankshaft, but it needs the movement. If you have very small movement or low motion, then the rolling bearing is not very good against vibration. And the best against the vibration are always the hydrostatic bearings, because then you can use the fluid pressure to carry the shaft, and there's no connection at all between the shaft and the bearing material. But if you need to consider friction losses, then the rolling bearing is better. The rolling bearing, as you remember, is sometimes called as an anti-friction bearing. And also rolling bearing is better if you have very small axial space. But in radial space, sliding bearing would be better. But of course, there are some rolling bearings that can handle both axial and radial loads, which on the other hand, sliding bearings do not. So as we can remember last time, if you have a sliding bearing and you have both axial and radial load, you had to have different bearing elements. But like we discussed here previously, for example, this kind of tapered roller bearing bearing system can handle both axial and radial loads. These are some considerations that you might introduce when you think about the possible designs for bearing arrangement. And of course, like in any design of machine elements, you have to consider loads, direction. What is the direction? Axial, radial. What is the extent, the magnitude? Is it static or is it fluctuating? What kind of space you have available? Are there some requirements for alignment? What is the rotational speed? What are the requirements from noise, stiffness of the bearing system? Do you need to provide free movement through the bearing system? So meaning that does some of the bearing needs to be floating? And how do you assemble and disassemble and maintain the bearing systems? And while you are designing the bearing system, today we are going to go briefly through how the calculation procedure according to ISO 281 goes, but always refer to the bearing manufacturer's catalogs, because they provide the full information of the bearing in detail, and always you need to cover those books when you are designing a bearing catalog, not only my lecture materials. And they are easily available, I would say, pretty much from all bearing manufacturers. Here are some of them. So FAG or Schaeffler is providing there in the link below, and also Swedish SKF. And if you go to the, for example, American Timken company pages or Japanese Koyo, they also will show their bearing catalogs online. Load, the primary function or the primary characteristic for the bearing size. So the loading is the thing that defines the bearing size. And in the rolling bearing, the load capacity of individual bearing is increased with the number of rolling elements and length of area of the contact surface. So it's easy to understand that the more rolling elements you have, or the more surface area within the rolling element you have, the more you will have load capacity. Like in the picture here, you can see that we have a single row ball bearing. If you have a spherical ball bearing which is containing two balls, of course the load capacity is higher. And the most common normal type of ball bearing is so-called deep groove ball bearing. And that bearing type has very high radial capacity, and also in connection with some extent of axial force capacity. So that is the reason it's quite often used in general purposes. So it has very good radial load capacity, and also it can withstand small some amount of axial load as well. But then if we have higher axial load in one direction, then you could use angular ball bearing. And as we describe, angular means that this force line through the rolling element is in angle. So it's not perpendicular to the shaft, but it's in certain angle. And depending on this angle, that defines what is the proportion of the axial and radial load carrying capacity of the bearing itself. There are angular ball bearings with different kinds of angles, depending of the load.
So is the angle defined by the design of outer and inner ring and their groove?
Yes. So basically the height of this shoulder defines what is the angle in the contact area.
I say these grooves, the shoulders are symmetrical, right? Or
Exactly so. So basically, therefore, the single row ball bearing can carry load in both directions, but the downside is that because there's always needs to be certain clearance. So there's a backlash. So if the load is changing its direction, there will be a backlash or clearance in the movement, free movement inside the bearing, and that is not usually something that we would allow. Okay, then we can have a cylindrical roller bearing. So they have a very high radial capacity. Well, it says no axial. There's a little bit. Cylindrical roller bearing. I didn't have a spherical roller bearing at all, but spherical roller bearing is basically a 2 ball bearings in a row, but the outer side, the outer raceway is spherical. And could you imagine what would be the benefit of this kind of bearing system?
Maybe less load on the outer ring.
Yeah, perhaps yes, also. But
Movement.
If you think, for example, shaft deflection, what would happen in this kind of bearing if the shaft is deflecting a lot comparing to the single row?
This bearing will allow movement of the shaft?
Yes, exactly. So the spherical ball bearing system, it is allowing the free deflection of the shaft. Whereas the single row ball bearing, if your shaft is deflecting, it is quite rapidly, it's highly loading the other side of the bearing raceway in the top and the other side, the opposite side on the lower part. So meaning that the deflection is increasing the load into the bearing. Whereas in the spherical ball bearing, if the shaft is deflecting, basically it doesn't increase the load to the bearing itself. So that is the one extremely good property of a spherical ball bearing. And the same can be applied also to roller bearings. So here you can see in the right-hand side, we have a spherical roller bearing. We have also spherical surface in the outer raceway. But now we have rolls, and that when we have rolls, it means that we have again higher surface area and again higher radial load capacity. So the spherical roller bearings are the ones which have the highest loading capacity. And also the ability to accommodate shaft deflection. But also we can have a cylindrical roller bearing, which is like here. So it means that the rolls are straight, and the outer raceway and also the inner raceway, they are cylindrical faces. These bearings, they have a very high capacity in the radial direction, but basically no capacity in the axial direction. Okay, there are some versions of cylindrical roller bearings which contain a small shoulder so that it can actually carry a bit axial load as well, but it's never that much. And the main load carrying direction is the radial direction. And then we have the tapered roller bearing, which is in essence, it's quite similar to the angular ball bearing, just that the elements are rolls, so they're tapered rolls. So like angular contact ball bearings, also tapered roller bearings are provided with different angles depending what is the ratio between radial load and axial load. So the higher the angle, the higher is the capacity in either direction. And one type is also axial roller bearing. In Finland, in Finnish it would be called painelageri, meaning pressure bearing, which means that it's only carrying load in axial direction and no load whatsoever in radial direction. For example, passenger vehicle clutch contains this kind of bearing, but it could be with the balls, but nevertheless it's the function is the same. It doesn't matter if it's rolls or balls, but just that the configuration can only carry axial load and no radial load at all. And depending on your application, you will select the suitable bearing on your applications, and also considering the cost. So if the cost wouldn't be an issue, it would be worth putting spherical roller bearings in basically everywhere, but that would be quite inefficient.
But how about size? I think it also matters.
Yes, of course. Yeah, you're right about that. Also the size, so that this is of course longer in axial direction, and well, maybe somewhat longer in radial direction as well. And because you have multiple rolling elements, more rolling elements, you will have more friction losses comparing to single row ball bearing. Okay, it was good that you mentioned the space, because sometimes the available space pretty much determines what is the bearing type we can use. In many cases, ball bearings are often used when we have small shaft diameters. And when we have very large shaft diameters, I would say like more than 0.5 meter or so, they are often with roller bearings. And the reason is just that if you have a shaft which has a diameter of 0.5 meter, and then you input a roller bearing, a rolling bearing, a ball bearing, it will mean that the outside diameter of the bearing will be huge. So often these roller bearings are providing more compact design. And if your radial space is very restricted, you could use needle bearings. So needle bearing is a bearing where you have a very long and thin roll. Basically, it's a cylindrical roller bearing, just that this roll is very long. And these are being used, for example, in two-stroke engines. Like here you can see a picture of a chainsaw crankshaft configuration where you have this the needle bearings in between the crankshaft and the connecting rod. In the ends of the crankshaft, there are normal ball bearings. But if you would consider that here would be a ball bearing, it would mean that the size of the bearing would be far bigger. And when the chainsaw is revving quite highly, more than 10,000 RPM, then it would be more heavy, and other construction would need to be more sturdy also. So in this configuration, the needle bearing is the best option. Alignment, this we spoke already also a little bit. So if we have a shaft which is deflecting a lot due to large loads or some other reason that we need to provide deflection, it means that the bearing system needs to be adapting to the deflections. And then we can use these spherical bearings. And when these spherical bearings are very good against shaft deflection, there are certain bearing types like axial bearings, tapered roller bearings, needle bearings, and cylindrical roller bearings, which practically do not tolerate alignment error at all. So if you know that you have a machine where your shaft is deflecting a lot, or you have a clutch which will allow large deflections, do not use roller bearings or axial bearings in the next to those deflection areas, because they will be loaded in the manner that you cannot anticipate in the calculations. The main problem with the deflection is that the bearing is loading in abnormal way. And for example, here in this deep groove ball bearing, the bearing is loaded sort of sideways, so that here in the top area, this side of the raceway is loaded, and here in the downside here. And what is the actual force in the contact point due to the deflection, it's pretty much impossible to define. And therefore, it's not possible to include that in the calculation, and therefore you don't know what is the actual lifetime going to be.
So that's why we should use these cylindrical bearings, right?
Yes, cylindrical roller or cylindrical ball bearings in the applications where you have high deflections. But there are, of course, deep groove ball bearing, it can tolerate some deflection, of course. It doesn't break immediately. But if you have really high deflection, then you would need to select something else. Bearing catalogs give recommendations on the bearing sizes, how much angular misalignment each of the bearing types can and size can tolerate. So, but those are usually fairly tight. So it's I think mainly because of the safety of the bearing manufacturer against any complaints. So, but nevertheless, it will give some kind of guidance where this alignment should be with certain bearing types. Also, one consideration that you need to think is precision. It might be additional required, for example, in machining machinery, high precise actuators, and there are special precision bearings that are being manufactured for these applications. If you need them, they are of course more pricey. So if you can use standard off-the-shelf tolerance class bearings, you should use those and use the precise bearings only where you need them. Speed is of course a defining factor. Rotational speed is limited by the operational centrifugal forces in the bearing, which means tangential speed basically, and also the heat, meaning the friction losses and subsequent temperatures. In some cases, you would need to add a lubrication, meaning oil, just for the sole purpose of taking the heat away. For example, in the tapered roller bearings, if the system is containing large tapered roller bearings, they usually need to be preloaded, and the type of the bearing is creating a lot of heat. And the amount of oil which is needed just for the pure lubrication purposes is quite small for the bearing. It doesn't need that much. But the tapered roller bearing can introduce so much heat that you will need to put several liters per minute or even tens of liters per minute of oil just to get rid of the heat. And when you have very high speeds, 8,000 to 20,000 RPM, even high, in those applications, ceramic rolling elements are being used, because the ceramic rolling elements, they have two main benefits. First of all, they are smaller in weight, and also they are higher strength. So from both of these reasons, they can be spin much higher speeds than the steel rolling elements. And generally, axial bearings, they cannot handle as high speed as radial bearings, which is understandable because there's no radial load capacity. There's nothing to prevent them escaping radially other than the cage, and that is not usually strong enough in high speeds. Noise could be a driving factor in some cases. For example, in domestic appliance, I mean household equipment, noise could be a selection criteria. If you had to have fairly low, I would say intermediate noise in combination with reasonable price, you should consider deep groove ball bearing or angular ball bearing with a plastic cage. The plastic cage is usually the best choice against noise. When you have the cage which is made out of brass or steel, that will usually give some rattle. But when the cage is made out of plastic, it will be less noisy. Further on, even though if you had a bearing with a steel or brass cage, you can reduce the noise by preventing clearance. So you could apply a slight preload, for example, using springs, which prevent the inside clearance of the bearing to create a rattle. Stiffness is sometimes something you need to consider. stiffness inside the bearing. Now we are speaking stiffness of the bearing itself, not the shaft or the surroundings. And the stiffness of a bearing is defined by the rolling element shape and number of the elements. But usually the exterior parts, meaning the shaft and the bearing houses, they have much larger impact in the bearing system stiffness. And in that sense, you can draw a general rule that the preloaded bearing types, they are more stiff, and that is understandable because there's no clearance in them. They are always running in contact, like tapered roller bearings and angular contact ball bearings. And if you need to increase the stiffness of the bearing system, you can apply a tighter fit, which means that then you will reduce the operation clearance. But in these cases, if you do that, you have to be very precise on the lifetime calculation, because if you reduce the operation clearance too much, you will create additional loads inside the bearing, and it might destroy the bearing before its time. Free movement, as we discussed previously, there are some applications where you need to allow axial expansion, for example, due to temperature within the bearing. So you could sometimes use cylindrical roller bearing in that application so that it will provide the axial floating function. If we look at this picture, we can see this cylindrical roller bearing. We understand that this shaft is free to move regarding the outer raceway. So the rolling element can move axially within here, and it doesn't introduce any additional loads. So that is one option. Also needle bearings, of course, they provide the same. But if you do that, usually there is also clearance, and then you would need to consider again the vibration and noise effects, because it might be that when you have this kind of free movement inside the bearing, it could be that it will increase the noises and vibration. And I would say the normal way to provide a free movement is to provide a clearance fit in the bearing housing so that the whole bearing can move inside the housing. Then assembly and disassembly, which is in quite many cases, it's forgotten by the designer. But it's quite crucial to the lifetime of the bearing. And usually the bearings that you can assemble one part at a time are easier to work with, needle bearings and tapered roller bearings, because in those bearing types you can install, for example, the inner ring first, and then you just insert the outer ring and the rolling elements. But most of the bearings you need to assemble in one piece. And when doing so, it's very crucial to design the tools and the process in a way that there's no force going through the rolling elements during assembly. It's really crucial. So there shall be no force pressed or anything going through the rolling elements while doing the assembly, because if you do that, there is very high probability of damaging the rolling surfaces during the assembly, especially if they are using some kind of hammering tools or impact wrenches or such devices that are providing hitting to the bearing. They will very easily create small dents into the raceways, and then they will, even though you wouldn't see them or feel them right away, if there's even a small scratch or dent in the raceway, it will quite rapidly grow while in operation.
So,
yeah, Please go ahead.
Yes, sorry for interrupting. You said the only way to correctly assemble the bearings on the shaft is to heat the bearing and then heat, I mean, increase temperature so it expands and then mount it on the shaft.
It's not the only way. It's by far the best way, of course, because then you don't need to use high force. But the bearings are being pressed at location with hydraulic cylinders. But just that in those applications, the tool is designed so that it will press. For example, if you have a tight fit between the inner raceway and the shaft, the tool is designed so that it will press the bearing from the inner raceway, not from the outer raceway, so that the load would not go through the rolling elements.
So some force is allowed, but no like extra load. Some moderate force.
Was it the question that can you allow some force against through the elements, or?
Yeah, exactly.
I would say that no. So if you ask for a bearing manufacturer, they will say that zero load is allowed through the rolling elements while in assembly. Of course, it's not practically true that there is some resistance, but it's very difficult to control it while in assembly. So the process should be designed in a way that you don't need to apply force through the rolling element.
But we can apply force through the raceways, preferably inner raceway.
Yes,
correct?
through the raceway, and which raceway depends on which side you have the tight fit. So if you have a tight fit between the shaft and the inner raceway, and you are pressing the bearing against it, then you should put the force against the inner raceway. But if you have the tighter fit on the outer raceway, then you should be pressing the outer raceway.
Mm-hmm. Yeah, it's clear. So I saw a video where electric motor had made some bad noises, so to say, and when it was disassembled, it was found out that the groove of outer raceway of bearing was damaged. Can the pressing the rolling elements be the reason for this failure?
Yes, it can. It's been also in my background while we were producing electric motors. It happened that there was some improper handling or improper assembly, which caused very, very small dents in the raceway, something that we didn't find or see in our own testing when the machine was tested after assembly, but they were there. And when the machine went to the customer and they run it, for example, 1 or 2 years, these small damages evolve into a major bearing damage.
That makes sense. Okay, thank you.
And also not only force, but also scratches to the rolling surface. So appropriate tools is very important, and whenever you can, use heating and cooling to ease the assembly. And in some cases, it's especially if you need a very tight fit, it would be maybe easier to design the inner bore raceway so that it will be tapered. So then the main benefit is, of course, that it's easier to assemble, but also it provides a function that you can adjust the tightness. So by for example, in this picture, by tightening the shaft nut, you can adjust what is the tightness within the inner raceway. And usually this kind of system is done so that the clearance within the bearing inside from the inner raceway to the outer race, it's been measured. And from the clearance, we can see what is the sufficient tightness for the shaft nut. So we can quite precisely adjust the tightness for the bearing according to the operation conditions. Okay, then something completely else, which is not the rolling bearing, but it's a own kind of a bearing type. It's active magnetic bearing. And this is the most advanced type of a bearing. And basically it means that the shaft is levitating on a magnetic field. And the magnetic field is created with the electromagnet, and it's controlled with power electronics. So like in this picture, we can see that there's a electric motor which has a shaft which is supported from both ends with active magnetic bearings. And as you can see, the bearing modules are fairly big and fairly complex. And in addition to that, you have the active magnetic bearing. You also need some sort of normal or ordinary bearings as a safety bearings. In case for example, the power is cut, there would be no damage to the components. And these are used in I would say in special applications. Usually where the active magnetic bearings are needed are the ones where normal rolling or sliding bearings cannot anymore operate. So the speed is so high. Turbo applications, compressors, turbines. And everyone can understand that this kind of bearing design is very expensive, and it's more or less always designed to application. But one of the main benefits of this design is that because the bearing damping and stiffness can be controlled with power electronics, it can also provide a damping against vibrations. So if we have, for example, eccentric load due to the operation of the machine, we can use the bearing system to dampen the vibrations. So it's so to say, quite sophisticated method for controlling the rotational machinery. There's a company in Lappeenranta called SpinDrive, which is producing active magnetic bearing. If you're interested in it, you can see their webpage. I think it's a quite new company, but they are trying to develop new types of active magnetic bearings, which would be more cost efficient. Okay, then we go to rolling bearing lifetime calculation. So how the key question for a designer, how can I make sure that the bearings will last the time that is needed? And the learning target for this entity is to the ability to calculate the rolling bearings with respect to static and dynamic loading. It could be that we don't have enough time to go to the dynamic loading, but at least the static we can cover today. So regarding the bearing calculations, there is a main division between static and dynamic calculation. So whenever the rotational speed is less than 10 RPM, we usually speak of static calculation. Dynamic calculation isn't necessary. And this is the more easy calculation, and it gives a static safety factor S0. Whereas when we have a rotational speed more than 10 RPM, we will need to calculate this ISO 281 nominal lifetime, basic rating life, or extended calculation using the modified rating life. And this calculation, as a result, we give the bearing lifetime in revolutions or in hours, this L10 something or L5 something. But before we go into the calculation, as a designer, you should ensure that this arrangement is designed so that the calculated lifetime is a reliable result. So this means that because with this ISO 281 calculation procedure, we can only estimate bearing failure due to fatigue. So the fatigue in the bearing raceway and between the rolling element and the bearing is something that we calculate with this process. So if you have something else that will create the bearing to fail, of course the calculation cannot cover that. So this would mean that before you can do the calculation and rely onto the calculation so that this is really the lifetime for the bearing, you need to have a distribution of the loads which is unambiguous, so that it is clear. You know exactly from the statics or solid mechanics what is the load for individual bearing, and you know that there are no other deflections which would artificially create increased loads that you haven't been able to include in the calculation. Also, you would need to include thermal loads or other forced displacements, or so that they are controlled. If you cannot prevent them, you can control what is the amount of the magnitude of these forced displacement, and then you can introduce them into the loads, and then you can have safety against them. And also this bending and twist and eccentricity, so that they wouldn't address any additional loads. One of the most important is that lubrication conditions are as designed. Most of the bearings do not fail due to the reason that they would have the bearing would be selected improperly or the calculation will be bad. Majority of the bearings fail due to the reason that the lubrication has failed in one way or another, meaning that there are, for example, insufficient lubrication, there is incorrect lubrication, or there is some contamination in the lubrication, like dirt, particles, or water. Water is really bad. It's even less than 1% content of water in the lubrication will deteriorate the lifetime of the bearing. And also one important thing is that the bearing should not be too lightly loaded, because sometimes it's so that people think that if you get a bearing calculation lifetime for 150 million hours, then the bearing system would be good. No, it's not good. It will mean that it will be destroyed before the lifetime, much before. And the reason is that if you have that high calculation result, it means that your loads are very small for the bearing size, and that will in the end mean that the bearing doesn't function anymore in a way that it was supposed to be. So in a very lightly loaded bearing, it means that these rolling elements are sliding, not rolling, and that is something that it's not designed. So if they are sliding, then it will wear out far quicker than with a slightly bigger load when the rolling elements would roll as they are designed. And typically, a minimum load for a bearing is 1% of the dynamic load capacity for deep groove ball bearings and 2% for roller bearings. If you're above that, then it's then you're on the safe side. And also something we already spoke a bit is the assembly and transportation. So those are usually the places where the problems occur. So the engineers design the bearing system in a way, and there's a proper lubrication, but in the assembly, either the tools are not appropriate, or there's some possibility for careless assembler to assemble them in a way that you will introduce force through the elements, or other means, or in the transportation or storage, there's vibration, and therefore in order to prevent the transportation damage, you should always secure the shaft with some locking device so that there is no micro movement. If there's micro movement due to the vibration, for example, due to road transportation, that is very harmful for the bearing, because the small vibration where the rolling elements are at place, they don't rotate, but they are at place, and there's small vibration introduced, it will quite quickly drive away the lubrication film, which is very thin between the element and the raceway. Whereas when the bearing is rotating, it is all the time recreating the lubrication film. But when it's at place and there's a small vibration induced, it will drive away the lubrication film, and then you have metal to metal contact. And again, it will create small damage, and it could be that the damage is really, really small during the transportation. But when the machine is put into operation, this already started damage is then evolving to a full-scale bearing damage. So that is something that's occurring quite often. Okay, then how to calculate? Static calculation. Here is a calculation procedure for a deep groove ball bearing. And as we remember, static calculation is used when we have a rotational speed less than 10 RPM. So the step number 1 is to calculate the radial and axial loads using normal solid mechanics. And the designation for these loads is F0R for radial and F0A for axial. And the 0 stands for static. Then you will need to select the bearing type that you have been thinking about. If you don't know exactly what kind of bearing to use, you can select several ones and then do the calculation and then maybe change it into a bigger or smaller if needed. Then you will need to define so-called equivalent static bearing load, P0. And this equivalent static bearing load, P0, stands for combined load from axial and radial loads. So we don't use this F0R and F0A separately, but we combine them in a defined manner, and then we get one figure which we are then going to use in the bearing calculation. And the rule in the static calculation for a deep groove ball bearing, for some other bearings they could be different, but for deep groove ball bearings, the rule is that if the axial load in comparison to the radial load is less than 80%, then you can use purely radial load. But if the axial load exceeds 80% of the radial load, then you have to use this kind of combined equation where you will introduce 60% of the radial load plus 50% of the axial load, and then use this in the equation. But if you have the axial load less than 80% of the radial load, then you can just use the radial load only. Quite simple and straightforward. And then next step would be that you take the static load rating, C0, for the selected bearing from the manufacturer's catalog. So for example, from this link, you can find the SKF bearing catalog. And then you have all that you need for the calculation. You just calculate the safety factor, which is then the static load rating divided by the equivalent static bearing load P0. And then this value of S, you can then compare to some recommendation given by, for example, by the bearing manufacturer, like in this table. Depending on the operation condition, there are certain requirements for static load safety factor. Or it could be that the safety factor is given by the customer. They want to have certain S0 and then you apply that. And if you do not meet the recommendation or the requirement, then you just select another bearing with a higher P0. Or if your static safety factor is far higher, then it would give you the chance to maybe select a smaller and lighter and more economical solution bearing. So that is quite quick and straightforward process to do it. And I think that at this point, it doesn't make much sense to go to the dynamic calculation because our task is for static calculation. The task is in the last page of the presentation, but in here, let's do so that now you can do the calculation work for this kind of example. So your task would be to select and calculate a suitable deep groove ball bearing for a conveyor shaft drive side, which means this bearing over here. So here we have a shaft for a conveyor. We have a drive pulley for there's a belt drive from here, and the conveyor drum is here, and your drive side bearing is this one, and that is the axially locating bearing, meaning that we know that it will carry the axial load. We know that the speed is 8 RPM, meaning that you can apply static approach. Here are some dimensions, and you can do the solid mechanics calculation if you wish, but just that I've already given you the radial load in the bearing over here. So this is the radial force. So you can do the calculation using statics if you want, but this is the value you should use. And the other loads are which create this result are the radial load from drive pulley and the radial load from conveyor belt, and then axial load from the skewed belt drive. So the belt drive is something that you can have the belt in an angle. It doesn't need to be exactly straight. So in this case, we have, for some reason, we have axial load which is coming from the skewed belt drive, and that is 1 kilonewtons. Then we have also a torque, but that doesn't affect you anything in this calculation. Okay, so basically this load and this load are the ones that you need to consider in the calculation. And do the calculation according to this one. Use this link to get the PDF. If it doesn't work, just go to the SKF webpage and write down a bearing catalog or something like that, and you will find a link for the PDF. They might change those in every now and then. Okay, feel free to start.
Tuomo, can I ask you about my project work in a private room? Or
Yeah, I think we can do so that we can go to a breakout room now with you, so that let's just open them. Okay, hello again.
Hello. Tom, should we select diameter 2 for this shaft?
No, you don't need that.
Oh, so it's okay. It's unnecessary calculations. I thought we should do all this calculations like we did for like a couple of lectures ago.
Yeah, it's just it's the same example I've been using in many cases. There's also diameter 2 mentioned, but in this calculation you only need the bearing size, which is the diameter 1. So your calculation for this task would only be to perform the bearing calculation. So you can take this axial load 1 kilonewton and you can take radial load 1.223 kilonewtons and use those in the calculation of the bearing.
I'll put my answer to the chat if you can check it if it's right.
Okay, so there's some activity in the chat. I don't see your message now for some reason.
Okay.
Could it be that if you put it?
I'll try again. Yes, because you was in the
Yes.
breakout room when I post my answers.
Of course, the result depends on which bearing have you selected.
Yep.
So my selection was something that the safety factor was 3.85.
Okay, mine was something like 2.02.
Quite probable.
Yeah, but it's quite unclear for me what exactly do we calculate. So we can check the axial loads and the radial loads and axial loads, and then what's next? Because I don't.
Then
really
you
understand.
just a second. I will show the screen.
So we can select the static load safety factor.
That is something you need to calculate. So now you have your axial load F08, right?
Mm-hmm.
And you have your radial load F0R.
Yep.
And then you can calculate this ratio and check if it's less than 0.8 or more than 8.8. And depending on the result, you should use either this equation or this equation for calculating the P0. But you will eventually see that the F0 is more than 80%. So this is the equation you will need to use.
And then we just select the C0 from the SKF catalog.
Yes, then you select some bearing, and for that some bearing you get the C0 from the bearing catalog, and then you can calculate the safety. It's that simple.
But like, what's the result? I mean, so we know safety factor, it can be 2, 3, or 1.4 or whatever. So
yeah, it depends, of course, on the bearing selection.
How do we know if we did the right selection? Like, the more safety factor is, the better, or?
Well, that's a good question. So, for example, in here you can see some general rules about the static load safety factor, what it should be. Okay, now we have a ball bearing. And for example, if we have a normal operation with higher requirements for smooth running, it should be more than 1. There's nothing else. So I would say that a safety factor of above 1 would be good. But of course, if your safety factor would be like 20, then all right, it will be strong enough bearing, yes. But then the question is that there might be some other bearing type which is maybe smaller and would nevertheless fulfill the requirement, but not be that big or inexpensive. So if you are selecting something very big bearing, like a bearing with a diameter of 1 meter, it's quite sure that you will have safety factor more than 1, but then if the safety factor is 50 or 60, then it's unreasonably high.
So it's common sense. We should think about
Yes.
some numbers. Okay.
Yes. So as you can see in this task, you need to think of your own what would be a good result. I don't give it to you. I don't give you the bearing type. You need to check some options from there and find a solution that seems good to you. And of course, you need to have a reasoning behind it. Like in the project work, some cases like we discussed, for example, with Agusti, that I don't give you exactly what value of ultimate strength to use. You should have some reasoning behind it.
Sorry, I have some question related to the project work. Can in the background?
Yeah, there was also, I think Zdenek was also asking the same. So I think I will take first him and then you.
Yeah.
Okay.